Okay, so all right, let's get started then. So today I'm going to talk about this. Well, I mean, the specific topic would be generative adversarial networks, which is called GAN, and I'm pretty sure that a lot of people, at least a lot of students know what GAN is, like GAN architecture is. Maybe I should do a poll. So, who does any which should be the right type of poll? So. Who's never heard of GAN architecture before? So maybe I can like adjust the level of detail that I should about explaining what GANs are. So who has never heard of GAN architecture before? Like, or who's never heard of the concept of GAN, actually, to be more precise? Because the concept of GAN is very simple, actually. So maybe everybody's familiar and I don't have to go explain this in detail. All right, so I'm gonna wait for chats for like maybe 10 seconds. All right, so at least everybody's heard of GAN architecture. So maybe I should ask a better question. Is there anybody who would like me to explain why GANs are trained, like why it works, like the underlying mechanism of GAN, or is or is everybody like really familiar with why GANs are like how it was proposed and why it works and why it's like why it can generate like realistic images? Is everybody familiar with the concept? All right, I'm gonna wait for like 10 seconds again. Okay, interesting. All right, so I guess everybody's like, super familiar then. Yeah, okay, so very simple recap. I'm not sure if recaps are even necessary, but basically the philosophy is that we want to train a model that can generate synthetic, like realistically looking samples out of nothing, basically out of like pure noise, like Gaussian noise or like uniform noise or whatever, like out of pure noise, we want to be able to train basically a neural network, train a neural network that can map or translate or map a random image or random noise into a realistically looking sample. And the way you do it is you have a generator and a discriminator, and it's a game between the two. So it's like the game is that the generator wants to generate an image or, to be precise, a synthetic sample that can deceive the discriminator. And the role of the discriminator is to actually discriminate correctly whether the given sample is a synthetic one or random one. So the way you train is you alternatingly train the generator and the discriminator, and you need to have like a real set of samples and a synthetic set of samples that are generated by the generator. When you and the way you train the discriminator is a binary classification. The way you train a generator is also again a binary classification, but you just train it in an opposite direction. So that's why it has like a one is updating, one is basically ascending and the other is basically descending. So because one for generator, you want to trick the discriminator. So you want to train your generator so as to maximize the trick like rate. And when you're training the discriminator, you want to maximize the correct prediction, the correct discrimination. So it's one way you're ascending, the other way you're descending. And If so it's basically it's a competition between the two, and theoretically, if you reach a equilibrium, like you'll meet in the you'll meet in the half, like meet in the middle. The discriminator and generator will meet in the half where discriminator will no longer be able to discriminate the real sample from the synthetic sample. So that's the basic setup. And GANs are really like it's not a very stable architecture. The training of GAN usually it's kind of like a dark art. So you have to do a lot of trial and errors and stuff. But once you train it once you like train it properly, then you get a very high quality images. Or not high images. It's just you get a very high quality synthetic samples that are appealing qualitatively, at least. Quantitatively, it's not really. I mean, there's no like way to actually measure whether a synthetic samples that you generated are really realistic, because like there's no good way to measure that. So we'll talk about that in MedGAN, actually, how we can at least indirectly measure the quality of the synthetic samples that we generated. All right, so this is like 5-minute tutorial. We'll move on to the interesting stuff. Right here. Yeah. Right. So it's the title of the talk, or title of the paper, is generating multi-label discrete patient records using GAN. But the original title was generating electronic health records with GAN. But I thought that when people hear the word EHR, electronic health records, they usually think about like time series. And here in this work, we're not generating time series, because at the time it was like very early work, and nobody really knew how to like generate high quality time series data out of using GANs. I mean, it's still kind of an open problem. But anyway, so we, instead of calling this generating EHR, we're calling this generating discrete patient records. All right, so the motivation for this is pretty obvious, because though a lot of people who are interested in healthcare research are hindered by the access to the actual EHR data, because EHR data is some personal data, so there's a lot of privacy issue attached to it, and like depending on which government or which country you're talking about, there are varying like degrees of laws that protect or that prevent people from using electronic health records for research purposes. So yeah, as I said in the early phase of this class, it's really hard to get access to PHI in Korea, especially PHI, meaning like personal health information. So interestingly, in the United States, it's easier to get access to PHI. Like if you have a clear understanding between the ones that are sharing the data, which are usually hospitals or healthcare networks, and ones that are using the data, which is usually a research lab. If you have a clear like contract between the two, then there's not a lot of like hiccups in the process, in the paperwork. But in Korea, it's a bit more tricky. It's a bit trickier than that. So yeah, it's like, so in America, in the United States, once you have a contract, there is nothing stopping you from actually using the electronic health records or PHI in the servers of your own, basically the school server. Like it's okay to copy the PHI or EHR into the school server so that the students can like freely use the EHR, as long as you treat it safely, like put it into behind like a virtual network and stuff. But in Korea, that's like it rarely happens, basically. Like even if the hospital is willing to share electronic health records for research purposes to schools, the students or the researchers at school still needs to be in hospital network. Like you can't, like the hospital, the PHI or patient records can virtually never leave the hospital network. It's very, it's strictly, it's almost it's as good as impossible. So it's almost impossible. So if you're interested in, even if you have a contract between the two, like the school, the research facility, and the hospital, that the researchers can freely use EHR, they still need to come into, like, they need to visit the hospital basically, so that they need to physically be there and then take a look at the data and then do something there. And then when they leave the hospital network, they can no longer have access to the EHR. So it's a very, very inconvenient setup. So given that kind of situation, the motivation for this work is, why don't we just generate a bunch of synthetic data that looks real, at least statistically or qualitatively, so that nobody has problem accessing actual EHR data. Like as long as we have a synthetic EHR generator, then there's no privacy issue attached to it. Like if you're generating synthetic ones, there's nobody's privacy to infringe upon, because we're generating synthetic data theoretically. So if we have a realistic synthetic data generator, then no, there's no problem for privacy issues. There's no access issue for the researchers. So it's just like, yeah, it's kind of like a magical solution to a lot of, like, difficult situation in healthcare research. And it is interesting. It is still an idea that attracts a lot of healthcare researchers, both in the United States and Korea. For example, like big hospitals like Seoul National Hospital, Seoul National University Hospital, and also Asan Medical Center, probably Samsung Medical Center. They all have like at least one ongoing project to generate synthetic data. So, okay, let's dive into it. So yeah, so because of privacy concerns, past approaches to privacy concerns is you identify the EHR using perturbation method. So you try to like add some noise into it, but if you do it like, if you share a perturbed data, there's still like, it's derived from the real data. So there's like, you can still make some like privacy attacks to it. And the other option is generating synthetic data, which has not been realistic enough for machine learning tasks. So our focus is this one. So we want to generate synthetic data that is realistic enough for machine learning tasks. For you want to generate a bunch of synthetic data set, and then you want to train your classifier or prediction model based on that synthetic ones, which does not involve any privacy issues. And then once you've trained your model on the synthetic one, you can deploy it on the real ones. So that's the basic setup. So yeah, the name of the model is MedGAN, and we want to generate completely synthetic data using GAN, and we want two evaluation, both critical. One is we want to generate high quality synthetic ones. So how are we going to guarantee that empirically? Another is, are we sure that we're not like infringing upon privacy issues? Like are we sure that we are protecting the privacy of patients by using GANs, basically? Because in order to train GAN, you need real samples, because as I said, discriminator needs to discriminate between the real ones and the synthetic ones. So you need to at least have some amount of real data to train GANs properly. And by doing so, you're indirectly infusing the model with data information from real data. So you need to be really sure your generated data is not actually like just copying real data. So two modes of evaluation. One is guaranteeing high quality synthetic, like guaranteeing the realisticness of your synthetic data, and another is guaranteeing privacy preservation. All right, so so that would be the evaluation, and the basic architecture is very simple. There's discriminator and there's generator, as obviously. Okay. All right. So the notations are: X is the real data, which is just a. In this case, in this example, in this architecture, we're gonna treat X as a count data. So let me draw here. So when I say count data, I'm usually talking about like this kind of thing. So each row is a patient record. So this is P1, this is P2. So, and then there's a column here, here, here. This would be some diagnosis code 1. This is some diagnosis code 2. This is medication, and maybe some procedure. And this is counting. So you have, let's say you have like maybe a year or 2 years worth of medical records, and you want to aggregate. You want to have an aggregate representation of that. So the way you do is you basically count how many number of times each patient experienced certain feature or certain diagnosis, certain medication, certain procedures. So maybe DX1 2 times, DX2 like 4 times, RX1 0 times, and procedure like 2 times. Maybe for patient 2, maybe it's the other way: 4 2, maybe 3 0, something like this. So it's basically like a count statistics, and so this would be our X. So, oh, sorry. Yeah, so this would be our X here. So let's say we have maybe like, again, like 30,000 rows of 30,000 rows, and maybe about 600 number of features. So 600 being like 200 diagnosis codes, 200 medications, 200 procedure codes, and 30,000 being like you have 30,000 patient records. So this is our given real records, the real data. So this is our X. And as I said, the role of the generator is to convert a random noise, which is usually drawn from normal, like unit Gaussian distribution, or sometimes even from a uniform distribution, but some way to generate random noise. And then you want to have a mapper G that maps the random noise Z to some synthetic, some sample, basically. So the output of Z, so the output of G would be like X prime. So X will be the real, X will be the real data, and X prime will be the synthetic. Let's call X prime as the synthetic one. So it's synthetic. Synthetic data. All right. And there's the D, which is this discriminator. So as I said, the role of discriminator is there's sometimes, so randomly, sometimes it is given actual real data, and randomly, sometimes it is given fake data. So sometimes it's X, sometimes it's X prime. And we know which one is which, but discriminator doesn't know. So we train discriminator by trying to correctly discriminate this, like X being the real and X prime, like X prime being unreal. So that's the basic setup. And because we're dealing with count data, which is discrete values, this like nature of the count data is what makes MedGAN a bit different from previous GANs, where previous GANs are typically trained on pixel images. So pixel images being like, if we're talking about like black and white grayscale data, then each pixel will have a value between 0 and 255, but you typically normalize it typically normalize it to 0, like between 0 and 1. So each pixel in your grayscale image would be somewhere some value between 0 and 1. So it would be like a float value. So the very first GAN was trained on float values, but our data is discrete count data. So that's why we need some extra measures we need to take some extra measures. So that's where autoencoders come in. So yeah. So the autoencoder, if I ever talked, I don't think I've ever talked about autoencoders, but basically the architecture of autoencoder is, let me just erase some stuff. So you have the architecture of autoencoder is basically like this. You have a contractor, you have an encoder and decoder, or a compressor and a decompressor. So basically you're compressing your real data into a smaller, like into lower dimension. Like for example, let's say that you want to compress a single patient data, so which would be like 600 dimension. So this will be like 600 count data, and you want to compress it into maybe 64 dimensions, and then you want to decompress it back into the original 600 dimensions. And the way you compress it is you just use like neural network. So your neural network would have like an architecture that has input of 600 dimensions and output of 64 dimensions. And then the way you decompress it is, again, another separate neural network where the input dimension is 64 and the output dimension is 600. And the way you train your autoencoder is just, this is very simple. You want to train the encoder and your decoder such that I'm sorry for a very bad writing, is that let's call this x and let's call this x prime. So your x prime would be decoded information of your encoder of x, right? Obviously let's call this z, then let's call the compressed representation, the 64 dimensions, let's call this z. So this is z basically, right? Encoding of x is z, and then you decode it back to x prime. So you want your x prime to be as close as possible to x, and you typically use like mean squared error between the two. So this is how you train your autoencoder. So you by trying to match these two, this pair, you're basically training the parameters here and parameters here. So that's your autoencoder. So there's a because the GAN generators, the generator G, are usually trained to generate a continuous value. So I put an extra decoding step basically. So the output of generator would have like some continuous value. So you put that through I want to put that through a decoder so that it would be mapped back to like actual count value, like discrete values, because what's generated here are continuous, and you translate the continuous output through a decoder that will be a discrete. So here it will be count value. This would be count value. This would be float value. So you want to have a decoder that maps the float value back to the count value. And the way you do it is basically you want to have a decoder, and in order to have a decoder, you need to have an autoencoder. So you pre-train an autoencoder so that you can take a decoder. You can like train the encoder. So you pre-train a autoencoder using the count value here, which is in the next slide. So let's move on to the next slide. Right here. So you take a real value, the real patient samples, like 30,000 of them, and then you train an autoencoder just like this. So there's an encoder and decoder. And once you've trained it enough, once you've sufficiently trained it, then you will have a decoder. You'll have a decoder here, the decoder here, which is the same thing. You'll have a decoder that knows how to map some random, some like a latent representation, some continuous representation back to the count value, back to the counting domain or the discrete domain. So you have a mapper ready to go. So once you've pre-trained it, you will have you just take the decoder part and then use it. You just plug it on top of the generator, so that the job of the generator is much easier now, because without the decoder, the generator will have to generate the count value from the get-go. Like it needs to map the continuous noise Z to the count directly. So that would make the job of the generator harder. But if you have a decoder like plugged in on top of the generator, then the job of generator would be converting noise value, continuous like float noise value, to some other noise value. Then the rest of the job will be done by the decoder. So that makes the job of the generator easier. So that was the whole reason for pre-training an autoencoder here using the real data. All right. So that pre-training is a separate step. Is a separate step to the actual GAN training. So GAN training will be, yeah. I'm going to explain the GAN training now. So I'm just going to erase everything. And then moving on to the next slide. Right. So so the discriminator is the objective function of the discriminator is pretty straightforward, as I said before. So you want the discriminator. You want the discriminator to be as accurate as possible in predicting whether a randomly given sample is real or fake. So we know that whether the sample, the input to the discriminator came from here or here. We know that, so we can generate like a label, the ground truth label. So we're going to use. So it's basically the input to the D is basically just like a bunch of samples here, where this is the x's. So yeah, Salmar x, Salmar x prime, Salmar x prime, maybe 3x primes, x's basically, and the output is like, and the value for the label for discriminator is that this should be this. So yeah, so discriminators leave the here. We will send it. So actually, the real ones are ones, right? So this one's real, and this one's fake, and this one's real. I mean, this one's fake, this one's fake, this one's real, and this one's real. So we basically just like construct a mini batch of like binary classification samples that we can feed into the discriminator. And the job of this, the update of discriminator is using basically this formula here. So you want to maximize the probability of correctly predicting the real value, real images to the value 1, and we want to maximize the probability of correctly predicting the fake one, xzi, which is the x prime. We want to correctly classify this to 0. So this is what. So the whole like this formula is basically telling us that we want this to happen, like predicting this to 1 and predicting this to 0. So very straightforward for the discriminator. And moving on to the next one, the generator looks a bit more complicated than this discriminator, because this discriminator is just a single logistic regression function. It just gets input. It just receives input as a 600-dimensional vector, which is the real patient vector or fake patient vector, and they just maps that 600-dimensional vector to either 0 or 1. But for generator, it's a bit more involved, because usually in GAN architectures, generators have a more difficult time trying to beat the discriminator, because the job of the discriminators is so much easier than the job of the generator, because the job of the generator is to generate a realistically looking fake sample to trick or to deceive the discriminator. So the job description of the generators is way more complicated or way more difficult than the job description of the discriminator. So usually people come up with some heuristics to like balance that out. But what I did is I like how I balanced that discrepancy between this D and G is I made the G way more powerful than D, so, because G needs more more firepower in order to successfully perform the more difficult job description. So I'm giving G a lot of firepower by giving like batch norms and skip connections and so on and so forth. So I think I use like three blocks of this. So a single block consists of a multi-layer perceptron equipped with ReLU activation function and batch normalization, and there's a skip connection between the two. So anyway, so these are like some technical details so as to make the learning process of G easier. Like batch norm and this like skip connection, they are all used to make the learning procedure like learning process go way like learning process of G smoother. So it's helping the learning procedure basically. But I didn't use any of these techniques in D because D is already the life of D is way more simpler than the life of G. So you don't need to add like batch norms and skip connections to D because it's already the job is already just pretty simple for D. So that's why there's like a imbalance between the expressiveness of the or the technical like tricks that I've put into between like D and G. All right. Anyway, so of course the training function, the training objective of G is to basically trick D as much as possible. So before you were trying to you were maximizing the log of 1 negative dxz, but now you're maximizing d of x of z. So the direction is reversed. So here you're trying to generate xzi because your xzi is coming from the G. So you're trying to generate xzi to maximize probability of forcing D to say like 1, like forcing the outcome of D to be 1, like trying to trick discriminator to say that this is the xzi is actually a true sample. So that's, you can see like the opposite direction of the training procedure compared to here and here. Right, and as I said, you alternate you train D once, and then you train G once, and then you train D once, and then you train G once, and they take turns basically. So yeah. And okay, so this is not enough. So this whole thing is just the architecture, and this is not enough to generate a realistically looking synthetic samples, because as I said, we're not talking about like generating images. We're talking about generating count vectors, which is very different from images actually. So I need to talk about this for a bit. So images, which are two-dimensional matrix, and a count vector, which is again a two-dimensional matrix, has a very different semantic actually. So here in this in the 2D image, the relationship between here and here is it follows like a very natural like transition of pixel intensity. I mean, unless there's like a boundary or something. Like let's say you're drawing like a mountain or cat or dog, then it's very likely that the pixel intensity, like the red, blue, green, or maybe grayscale, in the grayscale value, like the value between here and here, the nearby or the neighboring pixels it's probably the change, the difference between the two is probably very small. It's very marginal because it is like there's like a continuing like pixel transition. Like if you say that this much is like a human like face, then you can like these values here are pretty. The difference between the difference of pixel intensity in this region would be minimal, and this region would be minimal. So that is why ConvNetU works so well for images. But in count vector, what's recorded here and what's recorded here, it's a very different concept. There's like nothing that ties between the two. I mean, there's always, of course, there's implicit relationship between this. Like if this is hypertension, if this is diabetes, then you can assume that there's some connection between hypertension and diabetes. But sometimes there are connections between the two, but sometimes there are no connections between the two. So this like not only the values are discrete, but the relationships are discrete as well in count vectors. So it has a very different characteristics compared to like images. So unless you use the fact that these are very different from this, the MedGAN wouldn't really work too well. So I'm gonna erase this. So here I'm introducing something called Minibatch Averaging to basically encourage MedGAN, the GAN architecture, to generate a more realistically looking count vector. So Minibatch Averaging is very useful for generating count vectors or binary vectors for that matter. So anything tabular. When I say tabular, it means that like rows are individual samples and columns are individual features. So I'm going to call it tabular. So when you want to generate tabular samples, Minibatch Averaging is very, very helpful. So anyway, so before I go into this, is there any questions so far? Like regarding the architecture and regarding the training procedure for generating synthetic electronic health records? Any questions so far? Nope. All right.
So, Professor, so before that, so is there any way to learn about the relation between the vector and vector, the additional or model for our what do you say, the artificial real data to learn between vector and vector?
When you say vector and vector, do you mean between the column and another column?
Yeah, it is.
So theoretically, so Minibatch Averaging kind of does that. So what I'm going to talk about, the technique called Minibatch Averaging actually does that, like injects that information into the MedGAN, the relationship between different vectors, or I mean different columns. The way I'm explicitly injecting that knowledge into MedGAN by using the technique called Minibatch Averaging. But theoretically, what would be ideal is if MedGAN or the generator learned the implicit relationship between different columns, different features, that would be the best case scenario, so that we don't have to inject that knowledge explicitly. So if generator is smart enough to pick up all the like implicit, explicit relationship between different features, then the generator will be able to generate very high quality synthetic tabular data, right? But that doesn't happen in reality, so that's why I'm going to use this technique called Minibatch Averaging. So yeah, a very good question. That question is the motivation for coming up with this technique, Minibatch Averaging. All right.
Thank you.
All right, so it's exactly what I just said. Minibatch averaging is the way to explicitly to teach the generator the relationship between different features or different like columns. So it's an essential part of MedGAN and can be used for any discrete variable generation or any tabular data generation. Doesn't require any additional parameters. So it's not a learnable thing. It's not a trainable thing. It's just a count. It's just a statistic information given to the generator. So what I do is I'm just providing the mean of the current mini batch to the discriminator. So all right. So this doesn't look very intuitive. So I'm going to give you an example. So is this a count vector? No, it's not. Okay, unfortunately, it's not a count vector. Okay, so instead of using a count vector, for example, I'm going to use a binary vector, for example. But it's basically the same thing. So count vector is you count how many times each feature happened to a patient. Binary vector is you just indicate whether something did happen or not to the patient. So let's say this column, this vector. Okay, I'm going to need a pen. Let's say this column here, or this feature, represents hypertension. So this is a diagnosis called hypertension. This part is this column is diagnosis named heart failure. This is diabetes. This is kidney failure. This is something. Wait a second. Why is there? I'm sorry. Give me just a second. Right. Okay. Yeah. This is some. Yeah. These for something like so. Yeah. Each column or each dimension represents some diagnosis codes, some medication codes, some procedure code, something at least. Right. And this is your mini batch. So you train your MedGAN by mini batch by mini batch, obviously. So let's say your mini batch consists of like 100 samples or like. So some number of samples basically. And so this is the first sample, this is second sample, this is the third sample, and this is your mini batch of real samples. So this is the real record. So as I said, when you train your discriminator, sometimes you need to give real samples, sometimes you need to give fake samples, right? So let's say this is your real samples, and then moving on to the next page. So what happens is you can, all right, so it's really annoying to switch back between like the pen mode and the cursor mode. So anyway, so as I said, this is your mini batch of real samples, and if you average, if you average the sample, the mini batch of real samples, dimension by dimension or feature by feature, then this is your mini batch feature. This is your mini batch average of your samples. So what this says is, in this real sample, in this mini batch of real samples, the occurrence probability or the chance of this particular diagnosis code, which is hypertension, chance of this occurring is 13%. And chance of this occurring in this mini batch is 20%. And chance of this occurring in this mini batch is 11%. You see what I mean, right? So it's a Bernoulli probability. It's a chance of occurrence. And we're talking about binary. This is a binary a sample. So this is basically a binary occurrence probability: 13%, 20%, 11%, 17%, 10%. And of course, you can apply this principle to count vector. So if this was count vector, then this would be your average count per feature, like some average count here, some average count here, some average count here. But for the sake of like simplicity, I'm just going to keep this discussion in binary format. All right. So this is your mini batch average of real samples, which indicates the occurrence probability. So the larger the mini batch, the size of the mini batch, the more accurate or the more realistic this probability will be, right? So if your mini batch only consists of like 10 samples, then this average probability, this occurrence probability wouldn't be very accurate. But if your mini batch consists of like 1,000 samples, then your probability would be pretty accurate. So let's keep that in mind. All right, moving on. Let's say, so there's something called mode collapse that usually happens in GAN architecture, which is that what is the easiest way for the generator to trick a discriminator? Like in generator's perspective, what is the easiest way to win the game? It is to generate one very realistic sample and then feed that to the discriminator all the time, right? Like that would be the sensible approach. That would be like basically that is like the cheating for generator. Generator just learning one very specific, like basically memorizing one very realistically looking sample and always generating that would lead to winning the game, right? So that's called mode collapse. So if that happens, then seemingly your GAN architecture, your GAN model is like training very well. But after you've trained your generator and you make the generator like generate synthetic samples, it'll always generate the same sample over again and again and again because of mode collapse. So in order to prevent that from happening, because the same thing happened to MedGAN. So before using this technique called mini-batch averaging, MedGAN was learning a very specific, realistically looking synthetic sample, just one sample, and then it was always generating that sample all the time to trick the discriminator. So in order to cope with it, in order to avoid this mode collapse from happening, is why I use mini-batch averaging. And again, so back to the average occurrence probability discussion. So if the mode collapse is so if this should happen, if mode collapse does happen to the generator, then it would always generate the same sample again over and over again. You can see here, it's the same, like it's always 1 here, it's always 1 here, it's always 0 here, 0 here, 0 here, 0 here. Maybe out of like one in like 1,000 times, there will be some noise that would distinguish, that would like that would make this sample a bit different from the other. But basically this is like the usual pattern that you see when mode collapse happens, like always generating a very, very similar looking sample all the time. So in this case, what would happen in this case if we were to average the occurrence probability for each dimension? Like what would happen? Then you can obviously, what would happen is something like this. Like all right, so where's my pen? All right, if the generator was suffering from the mode collapse, then when you generate a bunch of samples, like your mini-batch of fake synthetic samples, and you do an average counting, or if you count the average probability, occurrence probability for each dimension, then it would look like this. It would look extremely dichotomized. So it's because of the mode collapse, it's always either 1 or 0, or 0, 1, like 0, 0, like 1. Basically, the values would be very extreme. So compare, like so far so good, right? So if mode collapse happens, then your mini-batch average of fake samples would look very, very dichotomized, like it's either 1 or 0. So far so good, right? So moving on to the next slide. So this, all right. So there's a clear comparison between a mini-batch of real samples and mini-batch of fake samples when you average the occurrence probability dimension by dimension, right? So at least if you just count the statistics, you can readily tell whether your mini-batch is a mini-batch of real samples and your mini-batch is a mini-batch of fake samples. And the only way for if you provide this mini-batch average to your discriminator along with the sample, so your discriminator would be like, there's like a 600 dimensional sample, and again 600 dimensional mini-batch average. So this would be the average. And if you put this into the discriminator, then your discriminator will have a very easy time of predicting whether the given mini batch is real or not. Because if you look at this value and if you look at these values, you can really readily tell this is a fake one and this is a real one. And the only way for the generator to win this game, to trick the discriminator, is, the only way for the generator to trick the discriminator when you provide both the sample and the mini batch average the discriminator is to generate a varied, it is to not be in mode collapse, basically. So the generator must avoid mode collapse in order to trick the discriminator when we provide the mini batch average to the discriminator. Is my logic clear to everyone? Like, we're forcing by giving the mean value of each dimension to the discriminator, we're forcing the generator to at least generate samples, like diverse samples that at least follows the first order statistics, basically. When I say first order statistics, I mean the mean values, the average values. Right, so that is the spirit of mini batch averaging. And of course, you can readily extend this technique into giving the discriminator a second order statistics, which is the correlation or covariance between a pair of features. So that would be what I think it was Mr. Cheong Lee who asked this question. So how do we provide the generator the relationship between a pair of features? That is, in addition to giving, so let's say this is your 600 dimensional, like fake or real sample, and this is your 600 dimensional mini batch averaging. So this is your first order statistics, which is the mean. First order statistics, which is the mean value. You can give a 600 times 600 very, very long vector, which is 600 by 600 times as long as 600 600. So when I 600 is because your feature space is 600. So there's 600 features here, 600 features here, and you can calculate the correlation between each and every feature. So this is your variance, basically. The covariance of yourself is variance. So like this would be the relationship between the first feature and the second feature, which is like heart failure and diabetes. And this is your correlation between the first feature and the third feature. Basically, you know what I'm saying. This is basically a correlation matrix. So you can, based on your mini batch of fake samples and real samples, either fake samples or either real samples, based on your mini batch, you can calculate the correlation matrix just like you calculated your mean vector. You can calculate the correlation matrix, and then you can just flatten it to a very, very long vector, basically like 360,000, no, basically 36K, no, 360K, which is 360K. And this is your second order. This is your second order statistics, which is correlation. Or it could be covariance, depending on how you calculate it, basically. So if you put this into the discriminator, D, then you are forcing the generator to respect the second order statistics when it's generating the second order statistics of the real samples when it's generating the fake samples. So this is how you would inject the relationship between a pair of features to the generator. So I hope this makes sense. But in this case, all right, so Mr. Huenoyan, so in this case, doesn't the model depend too much on correlations? I mean, they are much more than original data in this perspective. Oh, okay, yeah, all right. That makes sense. So yeah, because the portion of your input to the D is like only this much is the real, only this much is the sample specific portion, and this is the first order statistic portion, and then this is like your 360,000 portion in going into the D. So let's see what happens. Let's see what would happen if you were to actually do this. No, this would still enforce the generator to generate a realistically looking 600 dimension, because this one and this one, these parts are not the output of the generator. The only thing that comes out of the generator, or the only thing that is the function of the generator's parameters, is this, directly this, and this comes out of this basically. So these information have dependency, all have like a one unidirectional dependency to the outputs here, and so this is basically computation. So in order to satisfy this portion of the D, they all need to come out of the 600 dimensions here. So either, yeah, I mean, there's no guarantee that the entire 360K dimensions would be respected when generating like this, when generating synthetic samples, but it would give some information into the generator. But I've never tried this before, so this is all theoretical. So it would be interesting if like somebody did an experiment with this idea, like giving this information to the discriminator, because theoretically it could work, but in practice I've never actually tried it. So so Mr. Oyeon Kwan's question is very valid. You never know, right? All right, so this is the gist of the technique called mini-batch averaging. And actually, the interesting part of MedGAN is the experiments, but we are only 4 minutes out. As I said, there are two things that you need to satisfy when you're evaluating. It is the quality of your synthetic samples, and whether your synthetic samples are actually privacy preserving. But so that is why there's like a very lengthy experiment section. But let's leave that to the next class actually. So we're only 4 minutes out. So is there any question so far with the mini batch averaging or just MedGAN in general? Any question before we end this class? 이거 좀 더 복잡해지는 경우는 없나요? So the question is, 그러니까 D를 조금 더 강력하게 만들어야 될 필요가 있냐고요, 가끔씩? 그 뜻인가요?
네, 로지스틱 리그레션 말고 좀 더 약간 더
네.
네.
네. 보통은 D가 G보다, 그러니까 예를 들어서 이제 이미지를 만들 경우에는 이제 이미지 뭐 DGGAN 같은 경우, 뭐 DGAN이었나? 하여튼 DCGAN이겠네. DCGAN. Deep Convolutional GAN이라고 이제 그게 GAN 바로 나온 아키텍처인데, 그거 같은 경우 이제 높은 해상도 이미지를 만들고 싶을 때 이제 그거를 이 GAN을 단지 뭐 멀티레이어 퍼셉트론이나 풀리 커넥티드 네트워크를 쓰는 게 아니라 컨볼루셔널 네트워크를 써야 되거든요. 근데 그게 D에도 그렇고 G에도 그래요. 그러니까 G도 컨볼루셔널 네트워크를 써서 이미지를 만들고, D도 컨볼루셔널 네트워크를 써가지고 그거를 분류를 해야 되거든요. 이게 이제 진짜인지 가짜인지. 근데 그때도 그때는 D가 로지스틱보다는 복잡하죠. 어쨌든 컨볼루션 뉴럴 네트워크니까. 하지만 그때도 D가 G보다 복잡해진 경우는 제가 뭐 이것도 뭐 벌써 몇 년 된 지식이긴 하지만, 하여튼 D가 G보다 강력해지는 경우는 별로 없어요. D 자체가 절대적으로 강력해지는 경우는 있어도 상대적으로 D가 G보다 강력해져야 될 필요성은 보통은 별로 없어요.
이 미니배치 에버리징 같은 이런 거를 D가 복잡하면 D가 이런 측면을 학습할 수 있지 않았을까?
그 약간 끊겨서 그런데 조금만 다시 설명해 주실래요?
D가 좀 더 복잡했으면 이 미니배치
네,
에버리징 같이 뭐 이런 통계적인 특성 같은 거를
네,
D가 학습을 해서 탐지를
네.
할 수 있지 않았을까 생각이 들어요.
아,
질문이.
네.
네.
네. 그러니까 이제 D가 강력해질수록 더 그만큼 G가 D를 속이기가 힘들어지죠. 통계적인
네네.
이거를 넣었을 때. 그러면 그만큼 이제 G의 인생이 힘들어지는 건데, 그래서
네네.
사실 이제 겐이 처음에 나왔을 때는 페이퍼가 이제 D는 강력할수록 좋다 뭐 이런 얘기를 하거든요. 왜냐하면 이제 D가 완벽해야지, 그러니까 D는 완벽하면은 그때부터 G는 D를 속이기만 하면 되니까 D는 그냥 웬만한 빵빵하게 만들어서 이제 굉장히 강력한 D를 만들고 그 다음부터 이제 G가 D를 속이기만 하면 되잖아요. 그때부터는.
네네.
그래서 이제 그런 의미에서 D가 이제 강력해도 된다라고 얘기가 됐는데 또 어떨 때는 이제 D가 너무 강력하면은 G가 아예 속이지를 못하거든요. D를 처음부터. 하여튼 뭐 이제 그런 문제가 있어서 이제 그거를 적절하게
네네.
사실은 이렇게 만들어주는 게 중요해요. 그래서
네.
그래서 이게 겐을 트레이닝하기 되게 까다로워요. 이게
네.
서로 약간 엇비슷하게 엎치락뒤치락 하면서 성능이 가야지 이게 잘 학습이 되거든요. G가.
두 개의 수준을 맞춰줘요.
네네, 그렇죠. 수준을 맞춰주는데 그게 진짜 힘들거든요. 그게 뭐
네.
어떨 때 수준이 맞고 있다 안 맞고 있다를 뭐 육안으로 보기도 힘들고 그걸 뭐 퍼포먼스적으로도 보기도 힘들어서 여전히 이제 처음에 겐이 나온 다음에 향후 한 2년 정도, 3년 정도는 어떻게 하면 이거를 트레이닝을 안정적으로 할 수 있냐 그 논문이 진짜 많이 쏟아져 나왔어요.
네. 감사합니다.
네, 또 다른 질문은 팀 프로젝트 때문에 겐에 대해서 공부하다 보니 페이크 데이터를 제너레이트하기 쉽지 않고 특히 시퀀셜 데이터의 경우는 어려워. 그래서 시도한 이유가 앞에서 개인정보 데이터 제너레이트 하려고. 잠깐만요. 페이크 데이터를 제너레이트하기 쉽지 않고 특히 시퀀셜한 데이터의 경우에는 그러니까 겐을 사용했을 때 성능이 높아질 수 있다는 게 겐으로 만든 데이터를 가지고 추가적으로 데이터를 이제 보강을 하거나 데이터 양을 불려서 모델을 학습하면 더 잘 될 거라는 의미신가요? 성우님?
그 그러니까 겐을 사용했을 때 과거에 뭐 무슨 대회나 이런 거, 그러니까 이미지 트레이닝 같은 경우에는 이미지 트레이닝 같은 과거의 대회나 이런 거에 대한 결과나 이런 걸 봤을 때 겐을 사용했을 때 그 맞추는 확률이 되게 높아졌던 거로 제가 봤었거든요.
네.
그런 게 아닌가요? 겐이 뭐 많이 이 효율이 되게, 그러니까 효율이라고 할까, 그러니까 효율이 아니고 성능이 되게 높게 나와서, 그러니까 잘 트레이닝만 된다면 다른 걸 사용하는 것보다 겐을 사용하는 게 성능이 높게 나와서 사용을 하려고 하는 케이스가 아닌 건가요?
근데 지금 사용한다는 그 의미가 그러니까 하이 퀄리티 겐을 이용해서 가짜 데이터를 엄청 많이 생성한 다음 그거를 이제 또 다른 모델 학습 데이터를 사용한다 그런 의미에서 말씀하시는 건가요? 아니면은 어떤 의미에서 겐의 성능이 좋다는 의미인가요?
그러니까 이게 그러니까 RNN 이렇게 사용하듯이 겐을 사용하게 되면은
네.
서로 이렇게 경쟁을 하면서 디스크리미네이터랑 제너레이터 이게 두 개 다 성능이 높아지기 때문에 그걸 다 트레이닝 다 끝난 다음에
네.
저희가 뭐 이제 예측을 하고 싶은 데이터를 트레이닝 된 모델에 넣으면
네.
확률이 높은 확률로 잘 맞출 수 있는 게 아닌가 해서요. 겐을 사용할 수.
근데 걔는 기본적으로는 그러니까 생성 모델이라서 그냥 네, 뭔가 이제 뭐 예를 들어서 뭐 하트 페일리어를 뭐 맞추고 싶다 아니면 뭐 몰텔리티를 맞추고 싶다 그럴 때 쓰는 모델이 아니라 그냥 어떤 리얼리스틱한 이미지를 만든 다음에 그거를 그게 사실은 끝이에요. 기본적인 겐의 원리는 그냥 굉장히 실제처럼 보이는 가짜 데이터를 만들기 위해서 쓰는 게 GAN이거든요. 그래서 그거를 뭐 하트 페일리어나 뭐 몰탈리티 프리딕션 모델에다가 바로 쓸 수는 없어요. 네.
네, 알겠습니다.
네네. 근데 이제 그거를 제가 방금 말씀드린 대로 뭐 예를 들어서 뭐가 있지 뭐 예를 들어서 하트 페일리어 프리딕터를 만들고 싶은데 하트 페일리어에 걸린 케이스가 숫자가 너무 작아서 이제 그걸 불리고 싶다, 양을. 그래가지고 그 프리딕터의 모델 성능을 올리고 싶다. 그러면 뭐 GAN 같은 생성 모델을 이용해서 불려볼 수는 있겠죠. 근데 이제 그 불린 데이터의 퀄리티가 좋지 않으면은 있으나 마나한 불린 데이터를 해가지고 이제 우리가 실제로 학습하고 싶은 그 프리딕터 모델의 성능이 올라가진 않겠죠. 이제 그런 얘기가 이제 다음 시간에 제가 그 얘기를 할 겁니다.
네, 알겠습니다.
네. And we'll ask the question, wouldn't preserving privacy much hinders the efficiency of the generative model? If so, why is that important? Actually, interestingly, in my experience, no. So I will explain this in detail in the next class, but basically what MedGAN learned to generate, which is the synthetic ones, you can't really learn knowledge of the information on the real data that was used to train MedGAN. So there's a real data that was used to train MedGAN, and we were wondering whether we would be able to learn anything regarding the real data when we look at the synthetic ones generated by MedGAN. And the answer is probably no. Like a very, very high chance no. It's almost impossible. So privacy preservation it doesn't really hinder the power of the generative model to that much, which is still debatable. I mean, it's a debatable topic, but it doesn't necessarily hinder that much. But again, then there's the question like how much helpful are our generators in real life? Like how much are they indeed helpful in real life? Like that's another question. So yeah, so the term efficiency of the generative model is debatable to begin with, but I would say, naively speaking, like without talking in a rigorous manner, like preserving privacy to some extent doesn't really hurt the performance of the generative model. So there's even like GANs that are called like privacy preserving GANs, or differential privacy preserving GAN. There's something called like that. Some model that is called, is that correct? Differential privacy GAN. Yeah, something like that. Something that has to do with like trying to you wanted to generate like you want to generate like sensitive information such as such as electronic health records, and you want to generate it in a manner that theoretically guarantees that your privacy is preserved, but it doesn't. In my experience, doesn't really work. Anyway, so yeah. Anyway, to answer your question, will not necessarily would be my like a single like very short answer. Is that all right? Thanks. Great. All right. Great. Okay. So if there are no more questions, I'll see you guys next Tuesday. Is it next Tuesday? Yeah, next Tuesday. All right. Thanks everybody. Yeah, it's like if anybody has questions regarding GANs, I'll stick around for like a minute or two. But if not, like yeah, bye everybody, and have a good rest of the weekend, and I'll see you guys next Tuesday. Bye.